Hello. In section 12.6, we are going to talk about various types of surfaces, just to get an idea of how equations can work in three-dimensional space. So we already talked about planes and lines, of course, but now we want to look at what happens if maybe we don't have just a linear equation. So we're not going to cover every type of surface, of course. There's a lot of different equations that can be out there. Mostly we're going to focus on two particular types. The first type we're going to talk about are cylinders. And note that we're not talking about cylinders in what you might normally think of, the conventional sense where you have say two parallel circles and then connected to each other. That's normally what you'd think of as a cylinder, but that's not what we're going to be doing here. Instead, a cylinder is a surface that is made by essentially just taking a line in three-dimensional space and moving it along some curve. So say we have some plane curve, we have some line, and this line moves along that curve. We call this kind of line a ruling of the cylinder. And technically these rulings can be in whatever direction we want, and as long as it's not in the same plane as this curve. But for simplicity, we are only going to be discussing cylinders where the rulings are parallel to one of our axes. So remember, we have our three axes here. We want our rulings to be parallel to one of these axes and have it follow a plane curve that's in the plane of the other two axes. So there, it gets a little bit more complicated in writing down the equation of cylinders that are not that way. The equation of such a surface will actually just be the equation of the plane curve. So let's say we have a curve in our xy plane. I don't know. Let's draw something here. Let's say that's our curve. It's in the xy plane, and all of the rulings are going to be perpendicular to the curve. You could say is taking it in the z direction, and so on and so forth. If this is our surface, if this is our cylinder, then what we'd essentially do is we take the equation of our curve, maybe it's say y equals some function of x, and that would be the equation of the cylinder because we allow the z coordinate to be anything. Essentially, for any point on this curve, if you take a point here, then just attaching a z coordinate specifies this entire vertical line, that entire ruling. And so when we do the entire cylinder, we're just taking all those vertical lines all together as our surface. So let's look at some examples. It'll be a little easier just to use GeoGebra here. In fact, we're going to be looking at a lot of different surfaces in GeoGebra just to make it a lot easier to get a picture of what these things look like. So let's just take a simple example. What is our simplest curve that we like to talk about that's not just a line? Well, let's just look at our normal parabola. Or in this case, it's a cylinder, where the cross section, the curve that it follows in the xy plane, is the parabola y equals x squared. So note here, if we look at any point on the curve, we just have all the z values above and below it. We would call this a parabolic cylinder. So normally we just kind of attach the term for the curve to the word cylinder. We could also take, say, our normal circle. Let's take the unit circle. Note here that it basically is the cylinder that we think of, except note that it does go on forever in both directions, both the positive infinity on z and negative infinity on z. It never ends. There are going to be situations, especially when we get to integration, where we might have this particular kind of surface, and then we bound it by specifying z coordinates that it can basically lower and upper bounds for our z coordinates. We would call this one a circular cylinder, or really, because we are only looking at ones where the rulings are perpendicular to the plane where our curve is, we frequently call this a right circular cylinder. Technically, all the cylinders that we're looking at here are right cylinders for that reason. And then one more example. I mean, hopefully by this point it's pretty clear what's kind of going on here, but I do want to specify one more thing. So here, I'm using the equation x squared over 4 plus y squared over 9 equals 1. That's the equation of an ellipse when you're talking in just 2 dimensions. So what we get is an elliptic cylinder. So here, the cross section of this thing is an ellipse, or an oval if you want to use the more conventional term. But kind of the one thing I wanted to mention here, and this is not really so important on how we're going to be working with these things. If we were to draw in a plane, I'm just going to draw on the plane z equals x times a constant, though my constant here is going to be maybe not so obvious. It's going to be the square root of 5 over 2. We get a plane that cuts through our cylinder. And if you kind of look at it, you might notice here that the cross section, it basically cuts a circle on our cylinder. So that circle is not in the xy plane, of course. But what you can kind of note from here is that you could think of our cylinder as we've drawn it as essentially being built out of circles, but at a slant rather than going just straight perpendicular to the plane. So in a sense, you could call this elliptic cylinder a circular cylinder as well. It's just not a right circular cylinder. So I just thought that was kind of interesting. You could even say, let's put in another plane. So z is x times that same constant, but we'll go ahead and, I don't know, let's add 3 to it. Maybe that's a little close. Let's make it a little bit further away. Something like that. So you can kind of imagine here, we've got 2 circles that are, whoa. Okay, don't do that, please. We've got 2 circles that are technically parallel to each other, though not directly, you can say not directly over each other, and then just the lines going from one to the other. You can kind of think of that as a cylinder, just kind of at a slant. A cylinder in the more conventional sense, but just kind of slanted over. Okay. So kind of returning to our first one. That's not the one I wanted. I want this one. This parabolic cylinder. So remember, we got this cylinder here by looking at the equation y equals x squared. So note that the equation y equals x squared, when we're working in a 3-dimensional context, is the equation of a surface. It's not just the equation of the parabola. It's not just the equation of a curve. In order to specify the parabola that we might be expecting, we might have to pair it with another equation. In this case, we'd probably just pair it with the equation z equals 0. Think of it as we're similar to how we work with lines, where when we wanted to use symmetric equations, we needed at least two equations to make it work. One equation only gave us a plane. The same is going to be true here as well. We cannot specify a curve in three-dimensional space with a single equation. Normally that just gives you a surface. And frequently curves can be thought of as intersecting two equations. Think of taking this surface and intersecting it with another surface. And it's sort of like how we dealt with our elliptic cylinder with one of our planes. We get the curve that is a circle, and that's just how we kind of have to do curves in three-dimensional space. Though we will look at slightly better ways of doing that using more parametric equations than what we're doing here. Though this is definitely a way that we like to specify curves. Next, we're going to talk about quadric surfaces. So this is the general term for any surface as given by a second degree polynomial in x, y, and z. So something with the form ax squared plus by squared plus cz squared plus dxy plus eyz plus f xz. And then of course we have these are all the second order terms, but then we also have the first order terms, or first, I should say degree instead of order. So gx, hy, iz, and then of course we can have a constant. So anything of that, the graph of any equation like that, of course with some conditions to make sure that it does actually have solutions. But any surface that is given by an equation like this, we can call a quadric surface. Now, working these in complete generality would take quite a while and really wouldn't be too helpful for us. Most of the time, when we actually want to be working with one of these surfaces, we'll have it positioned in such a way so that certain axes are parallel to our x, y, and z axes. And if it has a center of it, then that center is going to be positioned at the origin. So we can actually simplify this to two general types. So we could have something where, say, we still have all of our square terms. All the mixed terms here can actually be kind of incorporated into those using rotations, though it's a little bit complicated to actually accomplish that. And then we can actually deal with the linear terms, the degree 1 terms, by completing the square, which will essentially turn it into us moving the surface around. So we'll just keep our square terms and our constant term. That's one possibility. Another possibility is when we might have one or more of our square terms left over, but then we have a term. In this case, we're putting it as our z term. One of our variables doesn't have a square left over, but does have a constant term. Or I guess technically here we could even have the I be 0 and just have, say, ax squared plus y squared equals 0. Something like that. Sometimes those can be a little uninteresting. So we're not always going to keep them in these kind of forms. We'll actually go through some specific forms of these, and we'll get basically the book has a table of them that we'll get to. But first, before we even get to that, let's look at one particular example. Just kind of an idea of how we might actually go about graphing such a thing if we don't know what it looks like to begin with, and maybe even even if we don't have, say, a graphing tool for us, even though we are going to use GeoGebra to actually do this a little quicker than actually working it all out in detail. So here I have it in GeoGebra where I've set it up so that I I can have a slider where I can look at various z values, and for each z value I am graphing the equation that is given by replacing z with that number. So here, if I pick z equals negative 1.05, which is just what I randomly have it on right now, I'm essentially graphing the equation negative 1.05 equals y squared minus x squared. But I'm also positioning it so that my z value is at that point. This is what we might call a level curve, or you might call it a cross section. And to get a good idea of what the curve looks like, we might plot a whole bunch of these cross sections. And this is kind of an interesting one where every cross section is a hyperbola, if you remember conic sections. And well, every cross section except for, if I get, yeah, there. When b equals 0, we actually have a pair of cross lines, which is kind of interesting. Now, in general, if you're doing this by hand, you might actually just plot all these hyperbolas on the same x and y axes, and kind of think of it as a contour map, or if you're trying to look at the different elevations on a map, think that's what's going on here. But at the very least, you're kind of getting an idea of what the curve looks like, or what the surface looks like by just looking at various curves, because curves tend to be a little easier to graph. Now, in this particular case, I do actually have the surface itself, so we can kind of get an idea of how it actually looks relative to those cross sections, those level curves. So you can kind of see how it follows the surface there. We call this kind of a shape a hyperbolic paraboloid because, well, first of all, all the cross sections that we're looking at right now are all hyperbolas. But if we were to take cross sections that are vertical instead of horizontal ones, all of the cross sections will actually be parabolas. Might be a little hard to see that without me plotting that. So maybe let's put in something like x equals 2. So you can kind of see here, this is a plane that's cutting through our surface, and it's pretty easy to tell that that cross section is a parabola. So that's why we call it a hyperbolic paraboloid. We also like to refer to such a surface as a saddle surface, because you can kind of imagine someone just sitting at the origin with their legs draped to either side, and then most saddles kind of curve up to kind of hold you in place. So, kind of interesting little surface there. So let's kind of quickly go through the various types of quadric surfaces in the table that's in the book on page 875, or 877, sorry. Yeah, the section starts in 875, or 874. Whatever. The table is on page 877. And there's 6 different types that it shows, though I will actually note some that it doesn't really mention that are kind of not as interesting cases, or at least not as important cases. So let's just kind of go through some of them. First one we're going to talk about is the elliptic paraboloid. OI. The oid ending is frequently used in a lot of surface names. But an elliptic paraboloid is going to be the graph of a surface where you have something where like z over c is equal to x squared over a squared plus y squared over b squared. So you can kind of see here if you pick a particular z, then you're going to essentially have the equation of an ellipse. So the cross sections, or at least the cross sections when you have constant z, are going to be ellipses. So if we want to graph something like that, we could say, let's just make a, b, and c all equal to 1. So z equals x squared plus y squared, and we get a surface like this. Now in this particular case, we let a and b be the same thing. We made them both 1. So sometimes instead of calling this an elliptic paraboloid, sometimes we shorten this to just paraboloid. In fact, this is going to be a pretty frequent surface that we're going to use when we get to integration. Mostly because it's nice and rotationally symmetric. If we were to say, let's actually hide that one and do something like z equals x squared over 9 plus y squared. So here we're making b and c equal to 1, but our a is equal to 3. Now the cross section is actually an ellipse instead of just a circle, but it still kind of has the same idea. It's still kind of a bowl-shaped surface, just with a non-circular lip to it. Note here, we could actually use, instead of having z over here, we could have picked x or y to be the one over here, but this is just the same, using that same general idea where we picked z to be the one that's not the square. So in fact, this is kind of the example here where the I is a negative that we moved over to here. Kind of to go along with the elliptic paraboloid, we also have one that we just looked at before, so the hyperbolic paraboloid. So here it's very similar in equation. We have z over c is equal to x squared over a squared, and instead of plus y squared over b squared, we have minus y squared over b squared. And note here, c doesn't have to be a positive number. If c is negative, you can kind of take the negative and just swap the order of your x squared over a squared and your y squared over b squared. So you could have these in whichever order you want. But the equation, but that equation, the elliptic paraboloid, just kind of using the one that we looked at before, z equals y squared minus x squared. It's our saddle surface. And just different values of a, b, and c will kind of change the shape of this slightly, but it's still going to be the same general idea. So still the same kind of look to it. Next one we're going to look at is the ellipsoid. So whereas these first two were from our second general type, now we're going to be looking at ones from our first general type. So here we just have our x squared over a squared, y squared over b squared, and z squared over c squared, and we just set that equal to 1. So note here, because we're squaring a, b, and c, we're just saying that all the x squared, y squared, z squared have positive coefficients. And, well, if they're going to have positive coefficients here, we have to have a positive number over here. It has to be a positive 1. So that's the basic idea behind this. Of course, when we do this, if say a, b, and c are all the same number, we just have a sphere. So let's say if all of a, b, and c are just equal to the same number a, then we could move the a squared over to the other side, and we get the general equation of a sphere. In fact, we could say they're all r, say r squared. So the sphere is a special type of ellipsoid. And in fact, if we let one of the a, b, and c be different, but the other two the same, sometimes we also refer to the result of that as what we call a spheroid. So you attach that suffix of oid on the end of it. And we could get more detailed about that, but the idea here is that we have special names for these kind of things. But the shape of them is pretty standard. So let's look at. So I'm going to look at one of the spheroids. I'm going to let A be 2, but I'm going to go ahead and pick 1 for B and C. Let me zoom in here. So you can kind of think of this as kind of an egg shape, but obviously a little bit more symmetric. But you can kind of think of a sphere, but just kind of stretched in whatever along the axes in some way. In fact, if we looked at, instead of something like that, let's look at, let a equal 3 and b equal 2. So and c equals 1, so that we just have different ones for all of those. So here, now all the axes have a different stretch to them, but it's still kind of taking this a normal sphere and deforming it along the axes. You can kind of think of it as a little skipping rock, if you want to. Next ones we have are the hyperboloids. But there's actually two types of hyperboloid. So the first type we're going to say is of one sheet. And then we'll also look at a hyperboloid of two sheets. Probably could have guessed that in that title. But the hyperboloid of one sheet is going to be the graph of an equation with the form, say, x squared over a squared plus y squared over b squared. So it's very similar to the ellipsoid so far, but now instead of having a plus sign in front of the z squared over c squared, we're going to have a minus sign. And still equals 1. Of course, the main point here is that one of the x squared, y squared, z squareds, one of those has a minus sign, the other ones have plus signs. It doesn't really matter which one we have, except it'll change which axis of symmetry we're going to have in our particular graph. But I'm not going to write down all of those particular equations. Just be aware that that's really the key point here, is that one of them has a minus sign. So let's go ahead and graph one of these. Let's just let a, b, and c all equal 1 from our equation there. And we end up with something like this. So kind of note here that there's not really a difference between positive and negative here. It's just kind of where GeoGebra has chosen to make our z-axis go. It just expands infinitely outward as it goes to positive and negative z values. But the idea here is we've essentially taken a hyperbola and we've rotated it around the z-axis. Now get this kind of interesting shape. Of course, the cross section here is a circle in all these cases. That doesn't always have to be true. It was true just because we picked the same values for our A, B's, and C's. If we were to pick something like say x squared over 4, or wait, I was going to do x squared over 9 minus y squared and plus z squared equaling 1. So here, instead of putting the negative on the z, I put it on the y, and I have a different value for a. We get this thing where the cross sections are definitely ellipses. So this is not just made by rotating a hyperbola around an axis, but the idea is still kind of the same, just kind of stretched in a way. But note that the axis that it's going around, the green axis here, is the y-axis, and that's the axis that has the negative sign. We have the negative on the y squared, and so that's what the surface is actually going around. The hyperbola of two sheets is very similar. So just like the ellipsoid and the hyperboloid of one sheet, we still have our x squared over a squared, our y squared over b squared, and our z squared over c squared. But now two of these need to have negative signs. So the ellipsoid had everything positive, hyperbola of one sheet had one negative, hyperbola of two sheets has two negatives. Of course, we can't have three negatives, otherwise we wouldn't have anything that actually has a solution, because then we have a negative equals 1. But this obviously is going to be somewhat similar to the hyperboloid of one sheet, but it's going to actually have two pieces to it, sort of like the hyperbola in the conic sections. So here, let's go ahead and again take a, b, and c equal to 1. So x squared minus y squared minus z squared equals 1. We get something that, again, a hyperbola rotated around an axis, but this time it ends up in two pieces. So we're not rotating around an axis that goes between the hyperbola, the different branches of the hyperbola, but the axis that goes through both of them. Of course, we also don't have to use the same a, b, and c. We could do something like assume negative x squared over 9 plus y squared minus z squared equaling 1. So here the positive variable is going to be the y one, but now our a is equal to 3. And it's still kind of the same general shape. It's still cross sections across are going to be hyperbolas, but now the cross sections the cross sections like this are going to actually be ellipses instead. And note this time which axis kind of is our axis of symmetry, the one that's going through here, is the one that has the positive term. So the positive term here is the y squared. The y squared is our green axis. But if we go to the first one I did, this time because I picked the x squared to be the positive one, the red x axis is the axis of symmetry. All right, need another page here. Our next one, this is going to be a shape that you're a little bit more familiar with, the cone. This is it's going to be the graph of something where it's like z squared over c squared is equal to x squared over a squared plus y. Shoot. I'm not sure why it does that sometimes. It just kind of does it out of the blue. So hopefully you can just put up with it, because I don't really know how to solve it. But as I was saying before, we're going to be talking about the cone. The cone is another one that's going to be of our first general type. So we're going to have z squared, we're going to have an x squared, we're going to have a y squared. And we generally just go ahead and put these over a, b, and c squareds. But this time, essentially what's happening here is we do not have a constant term. Now that's mostly because we position this so that the center is at the origin and all that. But the idea here is one of the x, y, and z has a different sign than the other one, so we can move it to the other side, and we don't have a constant term. That's kind of the general idea. But if we were to graph something like that, again, we're just going to let a, b, and c all equal 1 for an example. So we're graphing z squared equals x squared plus y squared. And it has the conical shape that you might expect. This is actually the more general version of a cone that we think of more mathematically, and it's the cone that we generally use when we talk about conic sections. So remember, the different conic sections, the ellipse, the hyperbola, the parabola, are all cross sections of this cone when we use a plane at various angles. But now, of course, this is a circular cone. The cross sections are circular. We could also say graph z squared equals x squared over 4 plus y squared. So here, instead of all being 1, I'm picking a to be 2. And now, it's still a cone, but the cross sections are ellipses. But it's still the basic idea where everything comes to a point, but then as it fans out, we just have ellipses instead of circles. All right. Now, these are the 6 that the book has described in their table, in Table 1 on page 877. There are a couple that the book doesn't cover that would technically fall under the same definition of a quadric surface, but they actually turn out to all be types of cylinders. So I'm going to go ahead and just include a one here. You could have something like y equals ax squared. This is a quadric surface because it just involves squares and constants, but the graph of this would be a parabolic cylinder. If we were to graph something like x squared over a squared plus y squared over b squared, but then we don't have any z's, this would be an elliptical cylinder, or elliptic. Or if we do something like x squared over a squared minus y squared over b squared equals 1, this would be a hyperbolic cylinder. These are all technically quadric surfaces, but because we talked about cylinders before, the book doesn't really bother mentioning them. But I feel it's nice to see why we don't actually we looked at these 6 types before, but we didn't need to include these. And then there's actually a couple more that are going to be maybe a little weirder. Let's look at something, say z squared equals a squared times x squared. What do you think that's going to look like? So I'm just going to go ahead and pick a equals 1 again. But let's just look at z squared equals x squared. Turns out the graph of that surface is really just 2 crossed planes. You can think of it where x squared, or say z squared equals x squared is really just saying either z equals x or z equals minus x. Because if we take the square root, we have to deal with the plus or minus. So we end up with 2 different planes that are formed by those 2 equations. So crossed planes are included. And then, of course, by the definition the book gave, certain quadric surfaces don't actually have to have the the square terms. So technically something like z equals ax plus by is also a possibility, and of course this is just a plane. Or we could have actually written this as ax plus by plus cz equals d. We could have written it that way. But planes, under their definition, do count as quadric surfaces, even if they don't involve any squares. Though you might want to exclude the cross planes and planes, just because they kind of don't really need the squares to work. So, but of course, the other three cylinders I have listed here do need the squares to actually work. It's also even possible for the equation to result in only one point or even no points at all. Something like, let's say x squared plus y squared plus z squared equals 0. Something like that. The only solution to this equation is x, y, and z all being 0 to begin with. Because if any of these is anything other than 0, this side has to be positive and can't equal 0 anymore. But 0, 0, 0 does work, so you could say a point is a possibility. Or if we're being really annoying about it, we could say x squared plus y squared plus z squared equals -1, which has no solution at all. There's no way to pick x and y and z using real numbers that makes that work. This is, you could say, it's the empty set. I'm including these just to be a little pedantic, but the point here is, at least at this point, you should have a good idea of what possibilities there are with quadric surfaces. And these are generally the easiest surfaces to work with, though we will look at another broad kind of category when we get into functions of multiple variables in chapter 14. So it won't be for a little bit. In fact, we're going to be looking at curves before we start talking about these, about more general types of surfaces. Because we want to be able to look at we're going to be doing calculus basically. So we'll be doing calculus with curves coming up in the next chapter, and then in chapter 14 we'll be looking at the calculus of surfaces essentially. But for now, there's not really too much more to go into. We're just kind of getting an idea of what surfaces are possible. So hopefully that's been helpful, and I'll see you in chapter 13 when we actually start talking about curves in three-dimensional space. So I'll see you there.